In this video, we are going to learn how to graph complex tangent graphs, which is similar in many ways to graphing complex sine and cosine graphs. However, because the shape of the tangent parent function is different than the shape of the sine and cosine parent functions, there are a few differences that we need to tend to. So you already have a copy of the steps for graphing one period of a tangent graph, and it's on the back side of the sheet that had the steps for graphing one period of a sine and a cosine graph. Looking at the steps, again, there are a lot of similarities. So the first step is when you're looking at what equation you're graphing, identify the parent function shape and standard period. So, for tangent graphs, if we refer back to our initial activity in this unit, this is what the standard tangent parent graph looks like. And it doesn't have the wave shape that sine and cosine have. Instead, it's got almost this cubic-like looking shape, but it's not just one. It has multiple parts to it because we have an infinite number of vertical asymptotes. So anywhere that tangent is undefined, and if you recall, by definition, tangent of theta is equal to sine of theta over cosine of theta. So tangent is undefined anywhere where cosine of theta equals 0. That occurs at pi over 2, 3 pi over 2, 5 pi over 2, and that's why you can see down on the bottom of the screen here how often is the value of tangent undefined is at every pi over 2 plus n times pi, where n is an integer. So you have infinite number of vertical asymptotes. Because of that, there is another change to tangent compared to sine and cosine, and that is the length of one full period. So the length of one full period of a sine or a cosine graph is 2 pi. And we consider one full period of a sine or a cosine graph to be one full wave. In other words, peak to peak or valley to valley is a common way that people like to identify a full wave of a sine or a cosine graph. But with a tangent graph, one full period is between two asymptotes. So you can see in the middle of the screen here, you've got a vertical asymptote at negative pi over 2, another vertical asymptote at positive pi over 2, and you've got one full period in between those asymptotes. If you calculated that distance, pi over 2 minus negative pi over 2 is equal to pi. So the standard period of a tangent graph is 1 pi instead of 2 pi like sine and cosine. That is going to factor into how we graph these. The other thing that you'll want to recognize about the tangent graph is that you will have 3 important points to graph, which is different than sine and cosine, where you have 5 important points to graph per period. So the most important point of a tangent graph is right in the middle there, where the concavity switches from concave down to concave up. That point is literally right in the center of your period. Then to get your other points, we use what we refer to as elbows, and I'll get to that when we are graphing a complex graph shortly. The other thing to note is that if you're talking about domain and range of a tangent graph, the domain of a tangent graph is not negative infinity to infinity because you have an infinite number of vertical asymptotes that are going to occur. So the domain kind of looks weird down here, but x cannot equal pi over 2 plus n times pi, which is very similar to where tangent is undefined. So wherever tangent is undefined, you're not going to have x values there. We're not going to assess you on that notation, but it is important to know that the domain of a tangent graph is not negative infinity to infinity. The range, however, is, because if you were to scan the y-axis, you are always going to have every y value possible despite all of the vertical asymptotes. So there's a rundown of the parent graph of tangent, and that's the shape that you are going to duplicate when you are graphing complex tangent graphs. Not going to be the exact same though, because we can apply vertical shifts, horizontal shifts, still known as phase shifts. We can also change the amplitude, and we can have reflections and all of the things that we've done with sine and cosine graphs in the past. So if we go back to the steps for graphing one period of tangent, this second step here is really important so that you identify what the various things do to your tangent graph. So again, very similar to sine and cosine, we have A, B, C, and D values. And some of these are going to do the exact same things. In fact, all of them really do the same things. It's just you have to adjust for the differences in the parent tangent graph compared to the parent sine and cosine graphs. So starting with amplitude. Just like in the sine and the cosine graphs, the amplitude is the absolute value of A. So when you are asked for the amplitude, it is always going to be positive. If A happened to be negative, that would have the same effect that it has on sine and cosine graphs. You would have a vertical reflection. So amplitude, no different. It's the number out front of tangent there. If it's positive, then you have this shape. If it was negative, it would be reflected. So I can actually do that here. Let's just rotate this page. Literally, they would look, oh, no, I guess that didn't work, did it? No, it wouldn't look like that. Your entire graph would be reflected so that instead of your graph going from concave down to concave up, it would go from concave up to concave down. We're not actually going to have you do any of those on the initial worksheet, but we'll talk more about that in class. I apologize for my flipping of the screen there, only for it not to work. Regardless, the period comes from the b value again, but there's a little bit of a difference. We still calculate it doing the standard period over b will give us the period. However, the standard period of a tangent graph is pi, not 2 pi like it is in cosine and the sine graphs. So we still calculate the period using the standard period over b, but instead of doing 2 pi over b, we do pi over b. It's really important to note, as is stated right over here, that you still have to factor b out if it's not already factored out. So x needs to be by itself in this parentheses, and if it's not, you have to factor the b value out. Otherwise, your phase shift is going to be wrong. The vertical shift is still the c value, and it is what it is. So if it's a positive c, we're going to shift up c. If it's negative c, we're going to shift down c. So no changes there. The only thing to note is that c can either be added or subtracted out front here, or it could be added or subtracted on the end. Phase shift is still the opposite of the d value. So if you have a negative d value, then you're going to shift to the right that many units. If you have a positive d value, you're going to shift to the left that many units. It's also important again to note that b has to be factored out in order for your phase shift to be correct. There's a mention down here of how to graph the asymptotes, and hopefully this makes sense to you, but the left asymptote is going to be 2 interval spaces to the left of center, and the right asymptote is going to be 2 interval spaces to the right of center. So looking at the parent graph again, you can take one full period and you can break it into 4, just like we did with sine and cosine. But this time when we break it into 4, we're going to have the center in the middle, and then by breaking it into 4, those other 2 parts will give us the elbows that you'll see in a little bit here. So you're still going to take the full period and you're going to divide it by 4 so that you can use that to get your important points on your graph. Once you do that, you've got all the steps here, mentally gauging where the graph is going to be, drawing your axes, getting your midline, getting your elbows, all that stuff. But probably the best way to do this is actually look at an example. So we're going to take a look at the assignment that you guys have, and that is to graph the complex tangent graphing problems listed here. The directions ask you to graph one full period for each of these, and then label your axes accordingly without any breaks in the graph. So very similar to what we did in sine and cosine graphing, but obviously we're doing tangent now. So we're going to use number 1 here, y equals 2 times the tangent of 1/2 quantity x minus pi over 4 plus 1. So I'm going to go right to the solutions here and walk you through the solutions so you can understand where the various things came from. As always, the first thing you want to do is identify A, B, C, and D. So as you can see, my A value is 2. My B value, which was already factored out for me, is 1/2. My D value is negative pi over 4, and my C value is 1. After you identify A, B, C, and D, you're going to want to actually decide what do those things mean. So as always, amplitude is the absolute value of A. Since A was 2, the absolute value of 2 is still 2, so my amplitude is 2, and since the original A value is positive, there is no reflection over the quote-unquote midline for my tangent graph. So you can even see my full period here is concave down to concave up because there was no reflection. My period I calculate a little differently than sine and cosine. So instead of doing 2 pi over b, I just do pi over b because the standard period of a tangent graph is pi. So my b value is 1/2. If I take pi divided by 1/2, that's like multiplying by the reciprocal of the denominator, so pi times 2. So my period of this tangent graph is 2 pi. Just like sine and cosine graphs, I now take my period and I make a note to myself that the period divided by 4, which in this case 2 pi over 4 is pi over 2, this number right here represents where my important points are. Now in the case of a tangent graph, they're not all points. It's also going to tell me where my asymptotes end up. We'll get to that in a minute. Vertical shift is the C value, so since it's plus 1, that means my vertical shift is going to go up 1. And my phase shift is the opposite of D. So if my D is negative pi over 4, that means I'm shifting right pi over 4. Once I have all this, I'm ready to graph. So what I would suggest is the same thing I've been suggesting in class when we've been doing our sine and cosine graphing. And that is, you should label your x and y axes first and then graph afterwards so that you have all the values on there. So looking at my vertical shift, if it's up 1, then it's safe to say that on my y-axis I can just go by ones. So you can see that I labeled my spots here 1, 2, 3, -1, -2, so on and so forth. Now where did I get my intervals for the x-axis? Same exact way that we get them with the sine and the cosine graphs. So you look at this value here, your period over 4, and you look at your phase shift. And you find the least common denominator between those, and whatever that is, pi over that number is what you should go by for your x intervals. So the least common denominator of 2 and 4 is of course 4, which is why you can see on my x-axis my intervals go every pi over 4. So 1 pi over 4, 2 pi over 4, which reduces to pi over 2, 3 pi over 4, 4 pi over 4, which reduces to pi, so on and so forth, and then I also made markings in the negative direction as well. Once I had everything labeled, again, we're going to do the same things that we do for the sine and the cosine graphing. So the first thing you always want to graph is your midline, which is based off the vertical shift again. So up 1, I made a dashed line here, a horizontal line at y equals 1, and I labeled it my quote-unquote midline. Then you graph your amplitude lines. So if my amplitude is 2, I go up 2 and make my upper amplitude dash line, and I go down 2 and make my lower amplitude dash line. So my lower amplitude is at y equals -1, my upper amplitude is at y equals 3. From there, all I need to do is get 3 important points in my asymptotes. So the first thing you want to get is your most important point, which is the center of your period. So since our phase shift is right pi over 4, I go on my amplitude and I go right pi over 4. What's nice about tangent graphs is that center is always on the midline. So you just go to the midline and you go to your phase shift, and that's where your important point is. From there, all you need to do is get your elbows and your asymptotes. So what I would suggest is do your asymptotes first. So go 2 intervals to the right, so every pi over 2 is where our important points are. So I go pi over 2 and another pi over 2, and I make a dashed line. And then I go left, pi over 2 and another pi over 2, and make my other dashed line. From there I just need my elbows, which means I go to the upper amplitude and I go right 1 marking, pi over 2, and I make a point. And then I go to my lower amplitude and I go left 1 marking and make a point. Then you just connect through those in that nice smooth tangent shape and you are done. More to come with tangent, but for now, there's a breakdown of how you graph tangent.